What up, calculus students? Going to get into other derivative problems in lesson 4. What do I mean by other derivative problems? Well, we're going to look at the other trig functions like tangent, cotangent, secant, cosecant. We're going to look into some notational derivative problems, some higher order derivative problems, so lots of other stuff and differentiability. So what is the slope equation of tangent? Well, now that we have the quotient rule, we can actually turn tangent into sine over cosine, and we can use the quotient rule on sine over cosine. Slopes of the top times the bottom minus the slopes of the bottom times the top, all over the bottom squared. And we see that the top becomes cosine squared plus sine squared. The bottom's cosine squared. And if we remember the Pythagorean theorem identity in the unit circle, that cosine squared plus sine squared equals 1, we get that the slopes of tangent are 1 over cosine squared. And that is the same as secant squared. And this is something that we will have to commit to memory. Remember, we have to memorize some things. Let's try to memorize less and understand more. Really quickly, cosine squared like this is cosine of the value squared. So if I ask you like to plug in something into secant squared, remember you would find the secant of the value and then square it. I would do the same thing for cotangent, and we would end up with negative cosecant squared. Cool. For secant and cosecant, I am going to rewrite it as 1 over cosine, and I am going to use the quotient rule, even though like I have the number 1. I don't actually have to. Like we'll learn a derivative technique next lesson that will allow us to get this like a little bit quicker, but let's pretend we just write it as 1 over cosine. We take the slopes of the top and we get 0, if we're talking about 1 by itself, times the bottom minus slopes of the bottom times the top, over the bottom squared, and we end up with a sine over a cosine squared. Now, we could leave it as sine over cosine squared. However, we're going to split up the cosines into 2 different cosines, and we're going to realize that we have this 1 over cosine and the sine over cosine. 1 over cosine is secant. Sine over cosine is tangent. So all of a sudden we have secant x, and its slopes are secant x times the tangent of x. So it's like a product of 2 things. And if we do the same thing with cosecant, we would end up with negative cosecant cotangent. So now we have like all of the slopes of all of the trig functions, and just like some things to help us remember. I don't know if I want to call them techniques or rather just like observations. So maybe I say observations. And my observations are that sine slopes are cosine. Cool, positive. Cosine slopes are negative sine. Okay, I noticed that the cosine, the c, negative. Tangent slopes are secant squared. Cotangent slopes, the c, we actually get negative cosecant squared. Okay, so tangents, cotangents, very similar slope equations. Cotangent starts with a c, cotangent slopes are negative. Then we have secant, which is secant tangent. Cool. A product involving itself, very similar to tangents. And then we have cosecant, which is negative cosecant cotangent. So we realize that all the c's have negative slopes. We realize that cosecant and cotangent involve cosecant, tangent and secant involve secant. So maybe some things to help you remember these slope equations. Some simple questions could be like finding the slope or finding the equation of the tangent line. So let's find the equation of the tangent to tangent. Well, the slope equation for tangent is secant squared. If I want to find the slope at pi over 4, how do I evaluate y's slope at pi over 4? Well, we would rewrite secant as secant of x squared. Now, secant is the same as the reciprocal of cosine. The cosine value is root 2 over 2. So that means I have 1 over root 2 over 2, or I have 2 over root 2. Now, you can go ahead and simplify this if you wanted to, rationalize it to help you out, and you get 2 root 2 over 2, which is just root 2. So this becomes root 2 squared, which is just 2. Turns out the slope of tangent at pi over 4 is 2. Remember, for the equation of the tangent line, I would need a y-coordinate. The tangent of pi over 4 is 1. The slope of tangent is 2 at pi over 4. We can graph that and see its beauty, which I'll do. Well, you guys try to find the equation of the tangent line to cosecant at pi over 4. So go ahead and try that. Here is the tangent function. Tangent function. I have y minus 1 equals 2, x minus pi over 4. Bam. Cool. So it worked. For cosecant, cosecant of pi over 4, might as well get the y-coordinate out of the way. It's the same as 1 over the sine of pi over 4. Sine of pi over 4 is root 2 over 2, so we get that same value as the secant of pi over 4, which is root 2. The slopes of cosecant are opposite cosecant, cotangent. That means if I want the slope of cosecant at pi over 4, I need to take a product. I need the cosecant of pi over 4 and the cotangent of pi over 4. Cosecant of pi over 4 is root 2, so this is negative root 2. Cotangent of pi over 4 happens to be 1. So I'd get that slope is negative root 2. You'll try it at different values, but combining things, we'd have y minus root 2 equals negative root 2, x minus pi over 4. So cosecant and y minus squirt 2 equals negative squirt 2, x minus pi over 4. Bam. Okay, so fun. All right, well, for right now, we're going to do it because we can. But for the future, it's going to mean something. We'll dive into the meaning of it. We have taken these y equations. We have been taking their derivatives to find their slope equations. We have been getting that the slopes of f are like the derivatives of f. I'm going to use the other notation, the alternate notation, the dy dx notation for the slope of y versus y prime. So we're good with that. This is called a first derivative. Great. Why do we call it just the first derivative? Because we could, and again, for purposes of right now, we're doing it just because we can, but there is meaning behind what we are going to do. We are going to find the slopes of the slopes, and that would be noted as the slopes of the slopes, f prime prime, or f double prime. It means the slopes of the slopes. It's not an 11, it's just a tick mark. And it means the slopes of the slopes. We're going to call this a second derivative. Now, if you use the d dx notation, imagine we're multiplying this together. You could see you would have d times dy, and you'd have dx times dx, which is dx quantity squared, but for notational purposes, we don't put the parentheses around it, and we just say it's dx squared. This is a second derivative. Now, typically after two derivatives, for any number above that, we would use a number. Now, this number is not f cubed. This is denoting the third derivative. This is denoting the third derivative, or the slopes of the slopes of the slopes. Cool? And we can keep going. So, for right now, asking you different questions like, what is the third derivative at 2 if this is an equation that we get? Now, what we need to be careful of, and what we have to start paying attention to with this lesson is like, what is given to us? What were we asked to find? Well, we are given the first derivative. That means we're not going to take the derivative 3 times because we already have the slopes of y. We just need to take the derivative 2 more times. And it'd be a good time to practice your notation of if you dx, you'd get d squared y over dx squared. Use the power rule, nothing crazy here. Constants stick around unless they're by themselves. And then the third derivative is that, and the third derivative at 2 is what we're looking for. If you use this notation, typically we write like x equals 2 on the bottom. We don't really put the parentheses there. So we got 12 times 4 minus 36. So 48 minus 36 is 12. So that is the slopes of the slopes of the slopes at 2. Here, look at that. F double prime, second derivative. We want the slopes of the slopes of f, and f is secant. Now, what's really interesting about this problem is when you find the slopes of secant, you probably don't remember it already, but the slopes of secant are secant x times tangent x. Great. Well, what if I asked you for the slopes of the slopes? The derivative of secant x tangent x. Well, it's something that a lot of students will make a mistake on, is that on the first step, we're just, taking the derivative, no big deal. But now here, if I were to take the slopes of f prime, I need to notice that it is a product. And we now have to break out the product rule. The slopes of secant are secant x tangent x. That's the slopes of the first times the second, plus the slopes of the second times the first. So we use the product rule and we realize that we have this messy second derivative. We could simplify it just to show you what we can do. Tangent times tangent is tangent squared. We can write it like this or with parentheses squared. Secant squared times secant is secant cubed. Cool. So be wary of applying rules. I'm good. What is that? Just extra donuts? Donut holes?
Yeah, you want?
Yeah, I'll take a donut.
Yeah, I know you. Are you filming it?
Shout out to Ben. Shout out to Ben right here. What up?
Guys, brought donuts.
BZ has a test, their first actual test.
Yeah. Let's lock in.
Let's lock in. All right. Read the question carefully. The horizontal tangents to f prime. So that's when f prime's slopes equal 0. Oh my gosh. This is tricky. This is when f's slopes equal 0. So to find the horizontal tangents of f prime, we need to look at when the slopes of the slopes equal 0. It's a tricky question that is worded weirdly, but is something you may be asked to do. You have to pay attention to details. We take our second derivative, the slopes of the slopes. When are the slopes of the slopes equal to 0? We get 4. X locations. Cool. What are some other higher order derivatives? What's the 43rd derivative of sine? What? The 43rd derivative? Well, it's a fun thing to do. Start taking derivatives. Okay. Like, I know you don't want to do it, but like, I want you all to try. If you're watching this video, pause and try and see what happens. I'm not joking either. Start taking the slopes of the slopes of the slopes. And you should notice something fairly quickly. If cosine slopes are negative sine slopes are negative cosine slopes are sine. We are back to sine at the eighth, at the fourth, which means the eighth derivative is going to be sine, which means the 12th derivative is going to be sine, which means the 40th derivative is sine, which means this is going to be the 41st, this is going to be the 42nd, and this is going to be the 43rd. So really neat seeing this kind of pattern emerge of the slopes of the slopes of the slopes. Okay, this is the sixth derivative. Ugh, this looks gross, but watch what happens. Because this is a power that is a whole number power that is greater than 0, what we will find is that as we go down, the powers will start to go down. That's it squared. And then all of a sudden, the fourth derivative is 48. And then the fifth derivative and the sixth derivative will have to be 0. Cool. All right, next type of question. Differentiability. Having a tangent slope. We say a function is differentiable if it has a tangent slope at a point. Now, when do you not have a tangent slope? You do not have a tangent slope at a discontinuity. So, any jumps, no slope. Any asymptotes, no slope at that asymptote. Holes, no slopes. Cool. There's some other things. Because a vertical line doesn't really have a slope, its slope is undefined. A vertical tangent, though it's an important location, is actually called a spot where we are undifferentiable. Now, where do vertical tangents occur? There are functions out there that look like this, where it like gets super vertical. And this vertical tangent, though, like you can see it's a vertical tangent, we would say we don't have a slope there because the slope is undefined. Cool, that's another one. And the last piece is, and it's the idea of a limit, how you have to look from the left and look from the right. The last piece is having a sharp point. What do I mean by a sharp point? Well, a sharp point, if you look right there at this sharp point, you can see that if I looked at the slope from the left, it's going to be different than the slope of the right if I'm just kind of tracing right over there. So we'd say, we don't have a slope there because of this disagreement of the slopes from the left and the right. So we don't have a tangent slope at a sharp point. Another word for this is a cusp, but we're good. Now, a way to test you on your understanding of differentiability is by giving you a piecewise function. And we know that piecewise functions, could have jumps. So what we want to do with this piecewise function is ensure we don't have a jump and ensure that when we meet up smoothly and we don't have a sharp point. So there's like two things that need to occur for this piecewise function to be differentiable everywhere. We got to make sure the piece on the left meets up with the piece on the right. And then, I feel like I can do this better. You got to make sure the piece on the left meets up with the piece on the right. But when they meet up, we need to have them adjusted so that when they meet up and create this smooth connection so that we don't have this sharp point. Okay, so there's really two things that we have to ensure. We have to ensure that they meet up. Well, this is when we find the left-hand limit and the right-hand limit, and we make sure that those agree with each other. All right, so this is back to like unit 1. I'm going to plug in 2. I get 8a. This is 2 to the left, and then 2 to the right is going to be 4 plus b. Great. But I can't solve this, and I don't have any other equations right now. Well, the second thing is ensuring that we don't have a sharp point. That means when we meet up, the slopes of the left piece have to equal the slopes of the right piece. Well, we are going to look at the slopes to the left of 2 and the slopes to the right of 2. Cool? So we're going to look at the slopes of ax cubed. We're going to look at the slopes of x squared plus b. Now here's what's important. A and b are just numbers. They're just constants. This is a good thing to think about. Remember, constants stick around unless them by themselves. So the slope of ax cubed is 3ax squared. The slope of x squared plus b is 2x plus 0. B's slopes are 0 because b is a constant. Now this is the slopes for the left at x. This is the slopes to the right of 2 at x. I am looking at a specific x value, so I'm not really done yet. What I probably should do, and what I think I did last year, was the following. We have an equation for the y values, but we can also create an equation for the slopes at all x's. And that's kind of what I think I did last year, which I like, is creating like a slope piecewise. Cool. Now that we have this, maybe it's easier to say the slope from the left is 12a. The slope from the right is 4. That gives me a is a third. If a is a third, b is 8 thirds minus 12 thirds, which is negative 4 thirds. I'll show you actually what we just did. We have, can't really graph piecewise functions. A is a third. 1/3 x cubed. 4. X is less than or equal to 2. How do I do this? Ah, there you go. Now, let's pretend I didn't have that third there. Let's pretend I had the 1 there. Cool. So it stops there, right, at 2. And then I have x squared plus b. I'm going to pick a random b like that. Use crazy parentheses, bigger than 2. All right, so first of all, we see that we don't meet up. That's a problem. Now, if I like shifted this up to 4, all of a sudden we do meet up. So that's good. We meet up. But you can see that when we meet up, the slopes are not really agreeing with each other. They'll create this sharp point, which is why we had to find that this value is 1/3, which dropped my y value down. This value was negative 4 thirds, and that connects our two pieces in such a way that there's a smooth connection. And now we've created this differentiable function everywhere. It's pretty neat, in my opinion. So let's try another one. X equals 1. Well, we have the y coordinates everywhere. Let's have the slopes everywhere. We'll have the slope is negative 1, and we'll have the slope is 2ax plus b. Constants stick around unless they're by themselves. We want to make sure that the y's meet up, so I will look to the left and right of 1 for my y's. And I'll make sure that my m's agree with each other. So my y's will be 2 equals a plus b. My m's to the left and right is -1 from the left, and if I plug in 1, I get 2a plus b. Great. Let's use substitution, or we can use elimination. I'll use substitution. Let me solve for b. Substitute that in. I have -3 equals a, which means b has to equal 5. All right, let's double check. Let's check this out. If I'm talking about 3 minus x for x less than 1, and ax squared plus b, ooh yeah, ax squared, I got you, plus bx. Let's do a nice little piecewise guy. Okay, cool. If a is 1 and b is 1, we meet up. But we got to shift our a's and our b's so that when we meet up nicely. If we shift a to -3, okay, and if we shift b to 5, ba-bam. Not only do we meet up, but we meet up so we create this smooth connection. And that's really cool. Thank you, Desmos. Last one to do if you want to do, but I think we're probably good. Why don't you guys try this one by yourselves? I'll write up the answer really quickly. Cool. Okay, that's easy. And then over here, we get 0 equals -b. So b is 0, a is 2. A cos x less than 0, and x squared plus 2, x squared minus 2. Is it x squared minus 2 or x squared plus 2? X squared plus 2. That doesn't work. Oh, well, A's got to be 2, and B's got to be 0. There's B 0, and here's A being 2. Okay, that's bad. What did I do wrong? A cosine x. Oh, x squared minus bx plus 2. What? B is 0. A is 2. For x is less than 0. Ah, there you go. Sorry. Yeah, look. The two pieces meet up, and they meet up smoothly. Sick. All right, last things are called notational derivatives, or table problems. These really baffle students because you like taking the derivative of x cubed. You like finding the slopes of x cubed, it's 3x squared. This is less like what is the slope of this function and more like what is the slope of this concept. So here's what I mean. We're given a bunch of information in this table. We're asked to find h prime of 1, so the slope of h at 1, and h is just equal to f plus g. Well, the slopes of h would equal, okay, the slopes of f plus the slopes of g. Great, so that means h prime at 1, or the slopes of h at 1 would equal the slope of f at 1 and the slope of g at 1. Well, the slope of f at 1 is negative 2. The slope of g at 1 is 2. All right, I can just get 0. Seems easy enough. But then we go to this problem on the right, and it's like, okay, j prime of 0, and j is equal to f times g, and you're like, okay, j prime, j slopes is equal to f slopes times g slopes. And you are wrong. Why are you wrong? I hope you're thinking about this. You are wrong because it's a product. And if you have a product, you have to use the product rule. So j slopes are actually equal to f's slopes at x times g's y values at x plus g's slopes at x times f's y values at x, which means it's a lot more involved than we originally thought. We need f slopes at 0. We need g's y value at 0. We need g's slope at 0. And we need f's value at 0. So that's negative 12 minus 4, which is negative 16. Okay? So really, it's a way to like challenge you on your derivative rules. Do you remember your rules? And if you do, are you using them correctly? Constants stick around. So don't freak out if you see 2g. You'd say 2 sticks around. I just have the slope of g times 2 and the slope of f times 3. And we're going to go into our table and find that information and go. Just because you see a quotient doesn't mean like just slopes of the top divided by the slopes of the bottom. You have to use the quotient rule. Slopes of the top times the bottom minus the slopes of the bottom times the top, all over the bottom squared. Then you have to find all of these values from your table, plug them in, do some arithmetic. And it's really the arithmetic that students mess up on. So practice your arithmetic. Okay? But what if I just gave you a graph? And I didn't give you the equation. I just said, here's f and here's g. And I ask you, what is p's slope at 8 if p is f plus g? I'm going to move this up here. All right, well, p's slope, since it's a sum, is just f's slope plus g's slope. P's slope at 8 would be f's slope at 8 plus g's slope at 8. Well, how the heck do I find f slope and g slope? Thank you. Yeah.
Video.
Yeah.
My whole advisory donuts today. I'm the best advisee ever.
Look at that. You heard it from the source. Best advisee ever.
best
Yeah.
of-
Thank you. Thank you.
Yeah.
We all
Look,
really
I got
appreciate it.
sprinkles.
Oh, epic.
During free, I'm gonna be out here working on.
All right. So I'm here to help. Cool.
Whoa, he brought donuts too.
I know it's a big donut day.
Wait, how did I not see you?
Oh. Take a donut hole.
They're big.
Oh,
I already got a donut hole from Ben. Donuts.
No.
It's a donut hole day. Thanks, man.
I went this morning. Earlier this morning.
yeah.
Good luck on our test, guys.
Guys, stop distracting Mr. Messner while he's trying to
No, we're good. We're almost done.
podcast.
Here, Ben, you can help me. P of x equals f plus g. I'm trying to find p slope at 8. So I got f slope at 8 plus g slope at 8 because I just took the derivative of f plus g. How the heck do I find those values if I'm given like a graph of a bunch of line segments?
Well, I would do it by finding the slope at those points.
Okay, so that's 8. 8
Yes.
is right here.
Wait a minute. Yeah, you're right.
That's an x value, right?
So now you do rise over run.
Oh, it's a line segment. It's a slope that can be calculated by hand using our knowledge from, our
Ben.
algebra days, or for Ben. So what's the slope there at 8 of f?
2.
2. What's the slope of g at 8?
It is -2.
It looks like negative a half.
-1/2. Oh
Yeah, they're good. Now, what do we have to be careful of, Ben, here for q of x, which is 2 times f of x times g of
Oh.
x.
But you're gonna have to use the product rule.
Very good, Ben. Okay. Ben, everybody give a hand for Ben. Very good.
Bye guys. Good
Very
luck.
good. Yeah, you too. Product rule, because it's a product. Now here's what we have to pay attention to. This 2. Now the 2 sticks around. You can either do what I call kind of like bake it in. What do I mean by bake it in? Just let 2 be a part of 2f of x. And we can say the slopes of the first are the slopes of 2f of x. So 2f prime of x times g, plus the slopes of g are the slopes of g times the first. So like the slopes of the first times the second plus the slopes of the second times first. Or you could say constants stick around. So that means you could just say, all right, stay there, constant. And then you could say the slopes of f times g plus the slopes of g times f. Cool. Well, now we have more things involved, whichever way we do it. Let's work with the leave out. We need f's slope at 2, and then we need g of 2. What the heck is g of 2? We need g's slope at 2, and we need f of 2. What the heck is f of 2? Well, let's remember, plug in x's, get y's. So g of 2 is just the y value of g at 2. The y value of g of 2 looks to be 3.5. We probably should do a little bit more work to ensure that it's 3.5, but if the slope is -0.5, you'd be going down 0.5 over 1, so that's good. Slope of f at 2 is this slope of up 1 over 1, so that's 1. The slope of g at 2 is this -0.5. F's value at 2 is 7. So like, we have to put that work together. We'll have 3.5 plus -3.5. We actually get big fat 0. Look at that. And same thing for quotient rule. This is a good one to try. Slopes of the top times the bottom minus the slopes of the bottom times the top, all over the bottom squared. And then we just have to go up to 9 and find all of our information. So g's value at 9 is going to be 1.5 if the slope is down 1 over 2. It's also down 0.5 over 1 if I divide the top and bottom by 2. So down 0.5 over 1, we're going to have a value of 1.5 at 9. So I'll write it as 3/2. F's value at 9 is 8. F's value at 9 is 8. F's slope at 9 is 2. G's slope at 8 is -0.5. F's value at 9 is 8. Cool. So we get -4 minus 2 times 3/2 is 3 over 64. That's it. Fun little notational problems. All right. I'll see you for the homework video. Peace.